In today's class, we're going to be looking at ideas from Chapter 6 in the middle of the chapter. The wave behavior of matter, quantum mechanics and atomic orbitals, and representing those atomic orbitals. So first of all, let's review a few ideas from the previous class when we had Bohr's model of the hydrogen atom. That was based on three different postulates. The idea that the electron would be found in particular orbits, which were these circles, these rings around the nucleus, and that those would be the only spots where the electron could be found. According to classical physics, the electron should not be stable in an orbit, but in Bohr's approach, he just said that it was. Now, the electron wasn't necessarily fixed in one of those orbits. A photon could add energy and move an electron to an orbit farther from the nucleus, and then it would eventually return back downward towards the nucleus. When it was moving closer to the nucleus, then it would emit a photon, and that's what our spectrometer was measuring. That was Bohr's model of the hydrogen atom. It included the nuclear model from Rutherford. The line spectrum for hydrogen was an important piece of experimental data, and also the idea of quantized energy. Now, that was Bohr's model of the hydrogen atom. Another model, which was proposed shortly after, was de Broglie's model of the hydrogen atom. Many of the same features remain the same, except for this one over here on the bottom left. Instead of having a ring where the electron was found, now the electron is being depicted in this strange way as a wave. Let's see what that is all about. That's discussed in section 6.4 when we're looking at the wave behavior of matter. So the scientist associated with this is the physicist Louis de Broglie. He was thinking, well, we've seen that light behaves like a wave, but the photoelectric effect described it as a particle. Light seemed to have both characteristics, depending on the characteristics for the experiment, whether it was an aspect of how a wave can undergo interference or something that was supporting the particle description, like the photoelectric effect. Depending on the experiment, it seemed to reveal different qualities for light. Now, if a wave can be a particle, maybe a particle can be a wave. That was his thinking. Now, de Broglie's model here is going to treat the electron not as a particle, but as a standing wave. So what is a standing wave? Here's the depiction of a wave where we're going to begin it set in motion, and it's being directed towards this fixed object. It's being directed towards this wall on the right-hand side. So we see the wave moving left to right as it's approaching the wall. When it strikes the wall, it's going to bounce back. The wave, as it's bouncing back, is shown there in the blue feature, and then the overall wave, what the line actually looks like, those are the dots that are going up and down, up and down. So we can conceptualize this as if the wave is interfering with itself. There are aspects of the wave going left to right and aspects of the wave going right to left. Now notice how it seems to be setting up in like a pattern. The overall wave is going up and down, but there are particular spots where it seems as if it's fixed, where it's not going up and down at all. Spots like here, 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 here. Those are called nodes. Those are spots where the wave is as if it's not moving at all. The overall shape here, what's being set up, is a standing wave. In order to have a standing wave, certain conditions must be met. And that's what's shown here from the e-text. You have to make it so either half of a wavelength or a full wavelength or 1.5 wavelengths fit within that particular distance. If you do have that, then the wave sets up and it looks like it's stable. That's what a standing wave is. That's the idea that de Broglie was using. So he was thinking here, what if instead of having our distance being a straight line, what if it's around in a circle? And we're thinking about what standing waves could fit such that their wavelength would match that particular circumference. He's thinking of those waves as being around the nucleus. Really a fascinating idea. Now, it's fascinating, but a particle like an electron, could it really be a wave? That seems like a crazy idea. Here's his equation describing matter when it has characteristics of a wave. He would say that matter has a wavelength that's equal to Planck's constant divided by the momentum, the mass, and the velocity. This could be used to take any particle and figure out what its wavelength would be. Now, waves such as visible light, X-rays, sound waves, the things that we've seen in water, how they undergo constructive and destructive interference when they interact with other waves. Diffraction is a phenomena illustrating wave interference. So we looked before with a simulation how we could have waves interact and then this resulting interference pattern. Turns out that X-rays can be diffracted. That's a very common laboratory experiment. And remarkably, electrons can be diffracted too. If something exhibits diffraction, that means wave interference is taking place. So the entity has a wavelength. This is convincing evidence that de Broglie is onto something, that electrons, even though they're particles, can be diffracted. This sample exercise illustrates something that's important for us. The concept is important more so than the math. So within here, this is an application of de Broglie's equation. It's looking to calculate the wavelength of an electron. So when we calculate this with the different values, we find that the wavelength of the electron is something that we could measure. It's close to 1/10 of a nanometer. That's a scale that's not unheard of when it comes to measurements. But if we consider these everyday objects, football, baseball, golf ball, what about their wavelength? Everyday objects such as those, they do have a wavelength, but it is extremely small, way too small to be measured. And the reason why is because their mass is so much larger here than the mass we'd use for an electron. If the denominator here is huge, the wavelength becomes ridiculously small. So we can say that everyday objects do have a wavelength, but it's too small to be measured. Another implication of thinking about matter as having characteristics of wave shows up with Heisenberg's uncertainty principle. Now, in classical physics, we could describe a particle in terms of variables like its speed, direction. Classical physics is entirely deterministic. If we were to think about a scenario where we were going to strike a ball on a pool table here, at least in theory, if we knew all of the variables, how we were striking the ball, the friction of the surface, any resistance due to the air, at least in theory, we could put that into a supercomputer and figure out where all the balls would be after we made the shot. That's what it means to be deterministic. However, in the quantum world, there are cases where it's impossible to precisely know information like that. It's no longer deterministic. It's impossible to simultaneously know two particular measured values that go together at the same time. Two that we're interested in are the position and the momentum. What we see here within the expression, this is another one that we want to think about conceptually, but we're not going to do the math with. The greater the uncertainty we have in one of the terms, the smaller that we can have in the other. Their product is over a particular threshold value, however. So this is what it means to say that we can measure both the position and the momentum. But the more narrowly we measure one, the more precisely we measure one, the greater the uncertainty in the other. So what do you think? Does the uncertainty principle also apply for an object like a person? If you were seeking to measure your position, would the Heisenberg uncertainty principle be relevant or not? The best way to answer that would be yes, there is uncertainty, but it is not going to be at all relevant for a macroscopic object like me or you. An everyday object, the uncertainty we have in terms of measuring our position is nowhere close to being relevant because the threshold value that we're looking at here involves Planck's constant. So any uncertainty in measuring our position would be ridiculously small. However, what about when we're thinking about the uncertainty for something like an electron? It turns out that if we think about it, Bohr's model here, it violates the uncertainty principle because we're knowing precisely where the electron is found on a particular ring, and we know its energy at the same time. Heisenberg says you can't know both of those with that degree of precision simultaneously. So that's pointing us, again, to a new model. Okay, we're going to move beyond Bohr's model and consider Schrodinger's model. Within this one, the energy is going to be quantized, and we're going to know that precisely. If we know the energy precisely, the position is going to be ill-defined, and we're just going to have to think about that in terms of the probability where the electron is. Let's explore those ideas. So in 6.5, we're going to look at an introduction to quantum mechanics and atomic orbitals. If I look within the introduction here, I'm going to see that the Schrodinger's model includes both characteristics of the wave and characteristics of the particle when we're thinking about an electron. It's going to incorporate both of those features. We're not going to do any math with this equation, but we want to qualitatively think about the results. What do they tell us? And we're going to begin with looking at the simplest of atoms that we can, the hydrogen atom, where we have just one proton and one electron. So this first objective, compare and contrast atomic orbitals from Schrodinger's model with those from Bohr's model. Here's a depiction within our simulation for Schrodinger's model. We no longer have these distinct rings. The position of the electron is poorly defined. We see that strange description here, and we'll learn more about that. If we look at the energy levels, are these energy levels identical to the Bohr model? If not, how do they differ? One thing that's similar, I see n equals 1, n equals 2, 3, 4, 5, 6. That was the same as in Bohr model. I see that those energy levels are getting closer and closer together as n gets higher. That's the same as in Bohr's model. One difference I see, though, is instead of just having one energy level for n equals 1, n equals 2, n equals 3, I'm seeing more and more energy levels here. Okay? They're on the same n equals 2, the same n equals 3, but it's no longer the same pattern identical to what I had with Bohr. A lot of similarities, but not identical. Okay? So when I say a lot of similarities, not identical, the position now, where the electron is found, within Bohr's description, we called them orbits. Within Schrodinger's, we're calling them atomic orbitals. They are no longer giving us a ring where the electron is found, but instead we're thinking about the probability in space where the electron can be found. We can't say where it is precisely, but we can talk about the region of space where it is found. These atomic orbitals are going to include quantum numbers. Within the Bohr model, we had one quantum number, our principal quantum number n. Our shapes now are more complex, so we need more quantum numbers. We need more quantum numbers to describe the shape and the energy of these atomic orbitals. The quantum numbers that we're going to be using are n, l, m sub l, and m sub s. These are the quantum numbers that we have within Schrodinger's model. This table summarizes information about the different quantum numbers. We want to know the symbol and name for each of the four quantum numbers. We want to know what the quantum number indicates, how their particular allowed values lead to the atomic orbitals that the electron may occupy. So we want to know the names for each four, the symbol that goes with them, what are the allowed values, and then also what they indicate. This particular figure is a good way to summarize the different relationships. So I'm going to go slowly through the information here, but if I'm going too fast, let's pause the video. So within this one, I see, if we're thinking about the atomic orbitals for the hydrogen atom, this vertical axis here is the energy. This is the same way we've been thinking about the energy before. It's approaching 0, which is our description when the nucleus, the proton, and the electron are far, far apart. So the one that is lowest in energy corresponds to the electron being closest to the nucleus. Each of the different boxes here represents one atomic orbital. When we have groups of them, like this group of 3, those are called subshells. And the entire row that we have represents a shell. So we have a shell, a subshell, and then each of the boxes representing an orbital. If we look within the pattern for how these are placed, I see n equals 1, n equals 2, n equals 3. So this is similar to what we had within the Bohr model. I have this first column here where there is just one atomic orbital, one atomic orbital, one atomic orbital. Those all have L equals 0 as a quantum number. This next group here, these sets all have L equals 1. This next set, L equals 2. The different L values, those correspond to the names for the different atomic orbitals. This first column here, when L equals 0, they're given the letter S. When L equals 1, they're given the symbol P. When L equals 2, they're given the symbol D. So within each of the groupings here, this first column, 1s, 2s, and 3s, I'm saying the principal quantum number, and then the letter that corresponds to the L value. 2p, 3p, principal quantum numbers 2 and 3, and then the letter that corresponds to the L value, and the same thing here with the 3D. If I'm thinking about the allowed values, the principal quantum number begins at 1 and then goes up from there in whole numbers. So that's why we see n equals 1, n equals 2, n equals 3. The L value, which is for the orbital angular momentum, starts at 0 and goes all the way to n equals 1. So you notice right there when we're looking at the L value, it starts at 0. I can have a 1s, but I don't have a 2s. I don't have a 2s. I end up having a 2p, a 3d. Notice how the pattern's going along there. How about for the m sub L values? The m sub L values span from negative L to positive L. So if L equals 0, the m sub L value equals 0. When L equals 1, m sub L spans from -1 to +1. When L equals 2, m sub L spans from -2 to +2. Now I know I've shared a lot of information with you. Okay? See if you can put it all together. What do you think the n equals 4 atomic orbitals look like? Which of the boxes would we have there? How would they be grouped together? Discuss that. See if you can share that on a whiteboard. So these are the energy levels that we have for the hydrogen atom. We've seen how each of the boxes is an atomic orbital. We have L values, which corresponds to the letters that we use to designate different atomic orbitals. And we have our quantum numbers that go with it. We've discussed n, L, and m sub L. The last one to add to this is m sub S. It was discovered after Schrödinger first proposed his model that we can have 2 electrons within a given atomic orbital, but they don't have exactly the same energy. This could be thought of as the electrons having a particular spin. That's why it is called the spin magnetic quantum number. For now, let's just recognize that the allowed values for the spin are either +1/2 or -1/2. We want to put that together because a task that we often have is to think about what combination of quantum numbers are allowed. This is a typical question. Is a given combination of quantum numbers allowed? If we think back to the figure that we made just a moment ago, which of these combinations are possible and which ones are impossible? Give that a try. So I think this first one, n equals 3, is referring to a 3p atomic orbital. Case D is referring to a n equals 3, L equals 2, a 3d atomic orbital. And this final one is referring to a 1s atomic orbital. Those all have plausible m sub l and m sub s values. This example here for B, I like that it could be a 3s. However, if L equals 0, I can't have m sub L equal -1. So that part is incorrect. The second case right here, n equals 1, L equals 1, that's not allowed. I can't have a 1p atomic orbital. Similarly, I can't have a spin value of 0. It needs to either be +1/2 or -1/2. Looking at combinations like this and thinking about whether it's allowed or not, very typical exam question. If we're thinking about what these atomic orbitals now represent, how do we visualize them? How do we communicate their shape? We want to think about different ways of representing them, including contour models and the radial probability function. And I find that there's 4 key ideas to think about with this. The first key idea that we have is that there are going to be 3 types of atomic orbitals we use a lot in this course: s, p, and d atomic orbitals. So we need to know their shapes. We will also discuss and use f atomic orbitals, but you're not responsible for knowing what all their shapes look like. Second key idea. For our atomic orbitals, a larger n value corresponds to a larger atomic orbital. The third idea, atomic orbitals can have what are called nodes. A node, remember we saw those within our standing waves a few minutes ago. A node is telling us a region of space that has 0 probability of finding the electron. And then finally, the radial probability function. That's a way of thinking about the atomic orbitals that allows us to look inside the atomic orbital. Not just what the overall shape is, but what does the electron density look like inside? So that first idea, we want to know the shape of s, p, and d atomic orbitals. So this is from the pre-class reading. Take a second here. What would a sketch for an s orbital look like? What would a sketch for a d orbital look like? This is what's called the contour plot, showing the shape. This is given here for a p orbital. What would be for the s and the d? What would be the L value? And what would be the possible m sub L values? Share your answers on that. Give it a try. When it comes to an s orbital, okay, an s orbital is spherical in shape. It looks like a ball. The m sub L value is going to describe the orientation of the atomic orbital. An s orbital has an L value of 0 and an m sub L value of 0. It doesn't have a preferred orientation. It's just a sphere. If you turn that sphere one way or another, it still looks the same. When we're thinking about the p orbitals, L equals 1, and there are 3 m sub L values corresponding to 3 different orientations. The L value is telling us the shape. The m sub L value is telling us the orientations it has. For the p orbitals, there are 3 different orientations where we have these 2 different lobes along the x, y, or z axis. That's consistent with the 3 m sub L values. How about for d orbitals? L equals 2, and the m sub L values then range from -2 to +2. I see there are 1, 2, 3, 4, 5 different m sub L values. And here are the 5 different d orbitals that we have. Any one of these would be something that we could sketch for what its contour plot looks like. So notice the number of m sub L values gives us the number of different orientations that we have in space for that type of atomic orbital. The second idea, larger n value corresponds to a larger size. We really see that illustrated here when we think about a 1s, a 2s, and a 3s. All of these are spherical, but notice as the principal quantum number gets bigger, the atomic orbital gets larger. So take a second, share some answers here. Would you say that these different atomic orbitals have the same or different L values? Do they have the same or different m sub L values? As I look at this, these are all s orbitals. For an s orbital, L equals 0, so they all have the same L value. How about the same or different m sub L values? every s orbital has L equals 0, m sub L equals 0, so those are also the same. The feature that's different would be their principal quantum number, the n value. Here's a chance for you to make some sketches. So the first question is asking to sketch contour plots for two atomic orbitals. Have the two atomic orbitals have the same principal quantum number, the same n, but different L values. The second set of sketches, again, two atomic orbitals, this time have them both be p atomic orbitals. Have them have different n values and different m sub L values. These are great sketches to make, and you could share them on a whiteboard. Now, there's different ways that you could answer this, different sketches you may have made. So within this first one, this would be an example where we have two atomic orbitals, same n value, so roughly the same size, different L values. L goes with the shape. So one is a p orbital and one is a d orbital. This would be one option. The second one, we have two different p atomic orbitals, different n values, so we're going to have different sizes. Because remember, as the n increases, the atomic orbital gets bigger. Different magnetic quantum numbers, different m sub L's, that means they have different orientations. So one could be along the z-axis up and down, and one could be here along the x-axis. That's what it means to have different m sub L values. Now, you're not responsible for knowing the shapes of the f orbitals, but here they are. If we were to look at these, what quantum number must be different for this atomic orbital compared to the others in the set? So as I look at them, they're all roughly the same size, so I think they have the same n value. They're all f orbitals, so they all have the same L value. But what needs to be different must be the m sub L value, because remember, that's showing us differences in the orientations. So we have, in this case, 1, 2, 3, 4, 5, 6, 7 different orientations, because my m sub L values go from +3 to -3. Now, ideas 3 and 4, I think those fit together. So idea 3 is that when we're thinking about where the electron can be found, it's never going to be found at a node. And second, if we want to look inside the atomic orbital, a way of representing that is with a radial probability function. So here is a figure from the e-text. So this is showing a column where we have 1s, 2s, 3s. So each of the columns corresponds to a different principal quantum number. It shows how we can go from the wave function, which is given the symbol psi, square it to become psi squared. We don't really need to worry about that particular process, but it leads us to something that's very helpful, the radial probability function. The way to interpret these, it's showing where the electron has a probability of being found if we begin at the nucleus and then we move and we look outward. So within this, the x-axis, the 0 is where is at the nucleus. And as we move to the higher numbers, we're moving farther and farther away from the nucleus. The peak that we then have, that tells us where the electron can be found. So for a 1s atomic orbital, where might the electron be found away from the nucleus? Sure looks like it's quite often found about 1 angstrom away. This next picture here, the depiction for the 2s, where might be the most probable position for finding the electron? It looks like maybe now at 3 angstroms, 4 angstroms, 2.5. Or it could be found in this region closer to the nucleus. These dashed lines here, they're showing us the position where nodes are. So if I notice within here, there is a node for a 2s atomic orbital right by 1 angstrom. If I'm looking for the 3s, I see 2 different dashed lines. I have 2 different nodes present. Those are regions inside the atomic orbital where the electron will never be found. Final feature that I notice here is as the n gets bigger, as I go from a 1s to a 2s to a 3s, notice how the most probable distance is moving outward. That's another way of thinking about how the atomic orbital is getting larger. These pictures here at the bottom are interesting. These are ways of looking inside that particular contour plot. And it's trying to show that when we get our 2s, then we have this node present inside of it. When we reach the 3s, we have two different nodes present. And again, that's at these distances where I see dashed lines. Now, there's a pattern for the number of nodes that we have. The first time we have an s orbital, we didn't have any nodes present. For the 2s, there was 1. For the 3s, there was 2. And this pattern is going to continue on. We can calculate the number of radial nodes using this expression. The principal quantum number n minus the L value minus 1. So if we're looking at a 1s, n equals 1 and L equals 0, 1 minus 0 minus 1, that tells me there are 0 radial nodes here. Identify n and L for these other cases, 2s, 2p, 3s, 3p, 3d, and use that to determine the number of radial nodes. And then we'll look for a pattern. Here would be my work. So I've listed the n value and L value for each of the different atomic orbitals. What we find is the first time that we have an atomic orbital, the first time I have an s orbital, it's a 1s. The first time I have a p, it's a 2p. The first time I have a d, it's a 3d. The first time that I have a particular type of atomic orbital, there are no radial nodes present. The second time I find that, meaning the 2s or the 3p, I've now introduced a radial node, and that pattern continues. The third time I have it, like the 3s, you would notice that increase, so now I have 2 radial nodes present. So this picture here of the first time we have the atomic orbital with no nodes, and then it adds 1, it adds 2, that same thing is found when I'm beginning with the 2p or I'm beginning with the 3d. We're going to see that these internal features for the atomic orbitals, those are going to be important as we move on within the course. So a lot of ideas have been shared here. We've been in section 6.4, 6.5, 6.6. A lot of new ideas to put together. As time allows, let's practice a few applications within class.